This section deals with computing antiderivatives, something that I don't know how long in the course you'll spend, but at least half a week doing these things. And let me give you something to consider. Consider taking the derivative of cosine of the square root of x squared plus 1. Well, the first thing that you would do is, because you have a function inside of a function inside of a function, we're going to have to use the chain rule. The first thing you would probably do is attack cosine, and you would get negative sine of the square root of x squared plus 1, like so. But then you'd have to take the derivative of the stuff that was inside of there because of the chain rule. And then, of course, this little piece right here is due to the chain rule. Now I'm going to pull my equals over here a little bit. So we'll pull this negative sign back in. Now you don't do anything with sine anymore. It's all done. And the derivative of the square root, by now you probably know that that means we're going to have 1 over 2 times the square root of x squared plus 1. I'm going to fix that too because it almost looks like it's in the root. But then this had stuff inside of it as well. So we're not quite done yet. I have to do d over dx of x squared plus 1. And we end up with negative sine of the square root of x squared plus 1 times 1 over 2 times the square root of x squared plus 1 times 2x. Now, if you're a student of mine watching this video, if I give you a problem like this on a test and you stop right here, you're completely fine. I will give you full credit. In fact, it's completely easy for me to see that you followed the chain rule all the way through if you don't simplify your answers. So, anyways, I am going to simplify because I want to make a point. You would see that you would cross out the 2's. I could put the x and the sine of x in the numerator, and I can wind up with something like this. Negative, let me put the x first, x sine of the square root of x squared plus 1 all over the square root of x squared plus 1. Now, wonderful, all done and everything like that. Suppose I asked you to compute the integral, the indefinite integral, so I just want an antiderivative of negative sine, well, let me sneak that x in, negative x sine of the radical x squared plus 1 I think actually I could take these out. Let me take that out. If I make my division bar long enough to include the negative up there, I think I'll be fine. Now the question is here. If I gave you this problem and asked you to do this integral, would you be able to do it? Now remember, we had a section on antiderivatives and things like that, and the things you were given, I have a Word document here where I collected all of them together. If you look, these are general forms. So if I see an integral with cosine, it tells me to do this. One for sine, secant squared. All the trig ones, we don't have to do the power rule because we assume that that one was easy enough for you to understand. Let's see. We have e to the ax. We have b to the x, where b is something besides e. We've got the natural log one. Then we've got these arc trig function ones. So these are the ones that I typically require my students. I think there's 3 more arc trigs that I didn't have, but fortunately none of my examples use them. But anyways, if I look here, if I try to look through these tables and look for an x sine of anything, x times sine of anything over a radical, I'm in bad shape because nothing here does that. So what do? Well, we've invented, I have nothing to do with it, but what has been invented, so something like this is not found in the table. In fact, a lot of tables wouldn't have this anyways, even if it went to hundreds and hundreds of different formats. Even so, what we're going to do today will lead us to be able to do problems like this by taking a little bit at a time. I wouldn't expect you to be able to do something like this because, especially the simplifying, you might be able to work your way backwards from something like this. You might. It'd still be hard because you might not. If this were jumbled up, this is in order of when I did the derivatives. If that were jumbled up, it could mess things up. But anyways, let's do some examples to show you what I'm talking about. Start with the easiest ones we know of. These are ones that you probably know, or you'll end up memorizing because you do them so many times. Things like the integral of sine of x dx. That equals negative cosine of x plus c. Don't forget, on these integrals without lower and upper limits, that they are considered indefinite, or I've heard people call these things the most general antiderivative possible for this function. So negative cosine of x is definitely an antiderivative, but I could attach any number to it I want and it would still be the right answer. All right, let's move on to the next one. Something like this is easy too. X squared plus 1 dx. You know that you use the reverse of the power rule, so we get x to the third over 3 plus x and then plus c. Let's first do some integrals. That use the table. What happens is you use the tables enough, and then you'll start to see the forms appear, and you'll know what to look for. Let me show you what I mean. We're going to do it as an example. I'm going to concentrate just on indefinite integrals for a while, because after all, the fundamental theorem of calculus says that we have to find an antiderivative in order to evaluate the function, because we got to remember, you got to do that big F, and you got to do big F of B minus big F of A. Well, that big F is the antiderivative. So let's take a look at an example. So I have 10 over the square root of 7 minus 2x squared dx. Let me fix that 2 to make it look like it's really squared. Now, what I'm going to do, the first thing I'm going to do is probably strip this 10 out front, because none of the tables are going to have a multiple in there. So let's get that out front first. So 1 over the square root of 7 minus 2x squared dx. Now I'm going to examine the tables for anything that looks remotely similar to this. So let's take a look. I'm looking for 1 over the square root of something minus something squared. So, well, this is beautiful. I found it in a second. Right here it is. This says if I can get it in the form a squared minus x squared, then I can just write the answer. So let's take a look at mine. I think what I'll do, let's bring that over here. Okay. So I'll go ahead and put that in here from the table. So let's take ours and examine how close it is. The 10 is not a big deal. I'll keep it around so I don't forget it, but the real stuff is inside of the integral. So I have 10 times the integral. It doesn't matter, I'll put the dx on top if you want, not a big deal. I like to put the dx after it and put a 1 on top, but no problem at all. Alright, so let's see how close theirs is to mine. It looks like I have an A. I mean, you can do some creative stuff with numbers, but the biggest problem right now that I see is that here there's nothing in front of x squared, but down here there's a 2. Well, what I can do is I can factor that 2 out. I'm sorry, I can't do it with the dx on top. It just bothers me to death. So if I factor the 2 out, here's what I have left inside of there. 7 halves minus x squared, and the parenthesis, and I've got my dx. So I'm getting close. Now what I'm going to do is I'm going to pull that, it's now a radical 2. I can actually pull it out and get this. I can actually pull it out front now because it's just a multiple. I get 10 over radical 2, 1 over the square root of 7 halves minus x squared dx. Now I've got it, because now this is not an a squared yet, but I can make it an a squared because 7 halves is a positive number. I can do my a can actually equal the square root of 7 halves, because then I'll write it here down here. 10 over radical 2 integral 1 over the square root of 7 halves. I'm going to make it teeny, but look, squared minus x squared dx. Now look what we got now. Now I've got an a squared. See that? An a squared. So this says I can proceed directly to the answer now. Don't forget to have this stuff in the front, which is sine inverse of x over a. My a was radical 7 halves. So I'll have sine inverse x over a. So this equals 10 over radical 2 times sine inverse x over the square root of 7 halves plus c. You don't have to do anything more with it if you don't want. If you don't want to simplify, I really don't care. It's not a big deal. Most people probably can't stand this radical 7 halves being down there and might make it x times radical 2/7. I'm sure that I probably would as well, but this is fine. You get the idea. That's using the table, and you've got to do some creative things sometimes to make it match the entries in the table. Another example. The integral of 5 times secant squared of 3x dx. And the first thing that you should always do when at any of these things is strip out the numbers, unless they prove to be helpful to you, and you'll see later what I mean by that. Alright, so I'm going to look in the table and see if there's a secant squared. I know that there is, but you may not have that knowledge until you use the table some. So let me see, the integral of secant squared. Oh, the trig ones, here we are. Here we are. The integral of secant squared ax is 1 over a tangent ax. So this equals, my a is pretty easy in this case, it's just the 3. So I have 5 times, the integral then would be 1 over 3, or 1 over a tangent of ax plus c. And you can make that a 5/3 if you want to. Alright, this kind of problem is very interesting, because if I go to the table, let me see if I see the square root of anything. First of all, See, these are all trig. And it figures, I mean, there's square roots in these things, but my square root doesn't look anything like that. It doesn't. My square root's not in the denominator, so all of these don't help me at all. This doesn't help me either. So what do I do? Well, the idea is this. We know, I'll tell you one thing we do know. If it was just radical x, I'd be in shape, because that equals x to the 1/2 dx, and then I could use the power rule to rewrite this as x to the 3/2 divided by 3/2 plus c, if it was just radical x, but it's x plus 1. Now let me show you some things that students have done before I'm going to erase them off in a minute, but this is some of the things they've done. Some of the students, I guess, I want to think in sheer desperation, have rewritten this as radical x plus radical 1 dx. The cardinal sin of radicals is to break them across square roots. I mean sums. The cardinal sin is to break this across a sum like that. And so then they'll apply the integral of this piece and this piece. No, 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 no. I'll just erase it. It never existed. It's terrible. That is algebraic failure on a monumental level. Now what we can do is we introduce something called the U substitution. Now, this dx does a couple of things. One thing it does is remind you of what the variable is that we're integrating here. Sometimes you would have like, let me come back to some of these, like this a in here. You know that a had nothing to do with the variable, so it's just a number that was attached to x, and you understood that that was not what was being involved in the integration so much as it was secant squared was going backward a tangent. So the same thing goes here. If I had an ax, then this problem wouldn't be much different, to be honest. All right, so a U substitution works this way. I would try to let U equal something like x plus 1. And then, if I take the derivative of U with respect to x, I get 1. Now this is something that probably will drive you batty if you put too much thought to it. But what if I multiplied by dx? Or in other words, du equals dx. Give me a second and let me remind you of what a differential is. If I want to do a differential, du equals du over dx times dx. And you see what happens here is this part here is u prime. So if I want to do with respect to x, so take a look here. Let me get rid of this stuff for a minute, and I'll rephrase it in that format. Actually, no, I'm going to leave it, but I'll write over here. The differential was defined to be du over dx times dx. Well, the du over dx in this case was x plus 1, so it's 1 dx. So it works both ways. The reason this notation, this differential was invented was to make the integral work perfectly, and so that I can rephrase it in terms of another variable. So I'm going to make our integral here look like this one here. Let me show you how. I have this right here. I've done a lot of talking since I've introduced the problem. So let me just come back here, rewrite the problem, x plus 1 dx. And I am going to allow u to equal x plus 1 like I said, and then du, remember, take the derivative of x plus 1, you get 1 times dx. So du just equals dx. So what happens then is right here where you see x plus 1, I'm going to replace it with u. So I get the square root of just u. And instead of dx, I'm going to replace it with du. The variable of integration is irrelevant. The integral still works the same whether it's an x or a u. So, but now, check this out. I can now use the inverse power rule and rewrite this as u to the 1/2 du. Which we know, according to the power rule, you add 1 to the exponent and then you divide by that new exponent. So I get u to the 3/2 divided by 3/2 plus c. Well, I'll do a little simplifying. I can't leave it just like this because I'm also going to put back what u was equal to, which was x plus 1. So that 3/2 down there becomes 2/3. And then in place of u to the 3/2, I will get x plus 1 to the 3/2 plus c. If I wanted to check myself, they always say to check, but nobody really ever does it. How can I check myself? Well, take the derivative. Well, when I take the derivative, the c, of course, disappears. This doesn't have much effect. It just hangs around. And so I'll bring the 3/2 down. So I'll get the 2/3 times 3/2. And then you'll subtract 1 from the exponent to get 1/2, which I think you'll understand is the square root of x plus 1. So that checks. Many times you'll approach an integral and you'll see things in it that look like the derivative of other things that are inside of it. I'll show you in a minute here as I write this example. Try the integral of 5x times x squared minus 1 to the 100 dx. Now, what I'm talking about here is, of course, you would not take this and multiply it all out. Although I have had students rewrite this as x to the 200 minus x minus 1, completely ignoring any rule of algebra they've ever encountered. I still think it's a good idea to factor out the 5 in the front, unless it helps us. Let's see what. So I'm not going to do anything because these use substitutions are a little bit different. Sometimes you'll get just the number you want in just the right spot. Trial and error is also involved here, so I'm not going to do trial and error. My choices have already been made. I've already done these examples ahead of time. I'm going to choose for my u x squared minus 1. Why would I choose that? Well, if I take the derivative, now if I do du equals 2x dx. Now, what I want to do is try to replace everything that has an x in here with things that only have u's. For instance, this whole piece is a u. But this piece here, this x and this dx, if you'll notice, is part of du. In fact, I will take this, since I don't see any 5's appearing over here, I'm going to factor out the 5. And I get 5 times x squared minus 1 to the 100 dx. Now I'm getting there. Now if I had a 2 in front of here, I'd be in business. However, what you can do is this. You don't have to manufacture a 2 here. I can divide by 2. Like so. And now, if I think of this integral in the following format, I'm going to rewrite it. You can do this in your brain after a while. If I rewrite it like that, take a look now. I've got my u to the 100 power, but then this part, this x dx, is du over 2. Well, this is no big deal. I'll just factor the 2 out front. Now it's a straightforward reverse power rule problem. So I'll get u to the 101 divided by 101 plus c. I think it's a good idea to put the plus c as soon as you can do it. As soon as you drop the integral, put it in there so you don't forget it. So I'll just multiply everything together. I will get 5. The u was equal to x squared minus 1, so I'll replace it. X squared minus 1 to the 101 divided by 202. And of course, differentiate it if you want to check your result. Let's do the integral of cosine of x times sine of x dx. Here we got lots of possibilities for u. If I allowed u to equal cosine of x, its derivative is negative sine of x, which is close. I can divide by -1. Even better though, if I let u be sine of x, du is exactly cosine of x dx. And I'll have a perfect integral. So, u is equal to sine of x, du is cosine of x dx. I will rewrite the integral so that you see how I'm thinking. I'll put my sine of x first, and then out back I'll put cosine of x dx. So you can see clearly, you can see that this part is going to be the u, and this part is going to be the du. And this is about as easy as a power rule problem as you can get. That's u squared over 2 plus c. And then I'll put my sine x back to get sine squared of x over 2 plus c. Let's try another one. Example, integral from of e to the 3x plus 1 dx. Now there's two ways I can think of doing it. Before I do the u substitution, I could, if I go back to the table of integrals, I see that this one right here deals with stuff of that nature. It has an ax, but I have 3x plus 1, so I have an ax plus b situation going on there. So what do? Well, what you can do, if you want to make it work, if you want to work the table for sure, you can remember your power rules and rewrite this as e to the 3x times e to the 1 dx. Then e to the 1 is just a constant, and you can bring it to the front. The e times the integral from, or I keep saying from because the definite integrals usually say from something to something. So I'll stop myself, I hope, from doing that. Now I can use the table because I've got a table thing like e to the 3x. Right there, the answer is 1 over 3 e to the 3x plus c. So this equals e times 1 over 3 e to the 3x plus c. Now if I wanted to, I could go back and put the e with it again, because after all this is still e to the 1, and the power rule, or the exponent rule, whatever it's called, tells you that you add the exponents when you put these together with the same base. So I'll have 1/3 e to the 3x plus 1 plus c. That is one way to get an answer for that. You're going to find that the tables will require more gymnastics than you're willing to do sometimes. So try this. I'm going to redo it. So we'll call this a big OR. I could let u equal 3x plus 1. Then du equals 3 dx. But you never do that. You don't, unless you see a 3 hanging around here. I don't want that, really. What I want is just dx. So I'll do du over 3. This way, I'm going to have an e to the u. And this dx is du over 3. So this equals 1/3 the integral e to the u du. But that's the easiest of all the integrals. E to the u, the integral of e to the u is just e to the u. So that's 1/3 e to the u plus c. And then I'll put the u back, which was 3x plus 1. So that's another way to get to it. What I'm telling you is in time, when you do integrals and you do integrals and you keep doing and doing them, you're going to probably do u substitutions as almost the first thing you always do. Let's try another example. Let's do the integral of x over x minus 2 dx. Now this may seem kind of odd. There's nothing in the tables that deals with rational functions. But there is something in the table that may help us a little bit, and I'll show you what it is. The only thing that deals with any kind of just a plain old fraction is this one, and you get ln of x. Now if you look at ours, all these are trig ones, so we'll stick with this one. The closest thing I have is this. This is something you'll have memorized in no time anyway, so I wouldn't worry about trying to memorize it. You do enough problems and it's just an automatic. In fact, this is one of the ones that people seem to know more than any other. All right, so come back here. I know that if I get a 1 over x situation, I'll know what to do. But with that in mind, I'm going to make the denominator the thing that I target. It's a good idea to do that. Why? I'll show you why in a minute. If I let u equal x minus 2, then du will equal dx. So the integral, let me just do the denominator for a minute. Du and dx are the same. But up here, I've got to replace x. You notice here, I have u equals x minus 2, not x. Well, this is not a big deal. U plus 2 equals x. So look what happens here. U plus 2. Now, it's in my favor because I can do this with it. I can write it as u over u plus 2 over u du. This is going to equal the integral of 1 plus 2 over u du. This is very easy to integrate. The integral, you can break this up into a sum of integrals if you want, or you can just integrate everything as they need to be integrated on the fly. So for example, the integral of 1 is u, and the integral of 2 over u is 2 times the natural log of the absolute value of u. Don't forget the plus c. Now I'll put my u back. What was my u? I forgot it. My u was x minus 2. So this equals x minus 2 plus 2 ln, absolute value of x minus 2, plus c. This is a correct answer. U, see if you can figure this out. Well, negative 2 is nothing but a constant. This is also a correct answer. You see what I did? I sucked the negative 2 into the c. Well, while I'm doing alternate answers, this is probably the best looking one, because then I took the 2 and used the power rule for the natural logarithm put up here. Well, if I'm taking things and squaring them, there's no longer a need for the absolute value, so this one will work too. This is the best looking one of all of them. This is the most simplest. I don't think that I would, if I was taking a test, I would leave it and not bother playing games. Let's take a look at the integral x over the square root of x plus 9 dx. And if, like I said, this u substitution business is a matter of trial and error, although the trial and error part of it decreases over time as you become more adept with your skill. But as you're beginning, you go to the tables, go to wherever you got to go to try to help you out. This right here you will not find in our tables. So hopefully you might think that letting u equal x plus 9 is a good idea. The good thing about it, one good thing about it, is that du is simply dx. So I will have, now that the last one sprang on, I won't have a u where the x is, I will have u minus 9. And in the denominator, I will have the square root of u. And then dx and du are the same. But I'm going to do the same thing I did before. Notice now I can break this apart into a difference of fractions. So I'll have u over the square root of u and minus 9 over the square root of u du. Well, this equals u over the square root of u is the square root of u. And 9 over u can be rewritten as 9u to the negative 1/2 du. And I don't really like to think of it as being u to the radical u. I think it's better to think of it as u to the 1/2. I'd like to apply the power rule. Square roots and any radicals are better for looks than they are anything else. So when I add 1 and divide by that, I'll have u to the 3/2 over 3/2 minus 9u to the 1/2 over 1/2 plus c. That equals, my u was x plus 9, so I'll get 2/3 x plus 9 to the 3/2 minus, is that a 9? That's a 9, so I get 18 x plus 9 to the 1/2 plus c. Let's try the integral of 8x plus 6 divided by 2x squared plus 3x dx. Now one of the things you might want to do is see if you can cancel stuff. Like I might try to think of factoring out, what can I factor out? A 2 out of the top. So I get 2 times 4x plus 3. And in the denominator, the best I can do is factor out an x. 2x plus 3. And that really doesn't do anything for me. So I'll just kind of leave this as a sad affair. Better left undone. You'll find yourself like a writer. You'll have a bunch of paper that you've balled up and thrown in the garbage because of this stuff. Trial and error, like I said. I'll try my u du stuff. And once again, I'll focus my u. The reason why I would focus my u in the denominator here is because when I take the derivative of this stuff, I get an x and I get plus stuff. So that looks like it might have something to do with the derivative of this. If not, I might be able to break this up into a sum of fractions, etc., etc. I got a lot of possibility. So I'm going to let u equal this stuff down here. So u equals 2x squared plus 3x, and du equals 4x plus 3 dx. Now, interesting. Factoring out that 2 may not have been a waste of time. Look at that 4x plus 3 sitting there. Let me have this integral back. So we have 8x plus 6 all over 2x squared plus 3x dx. Let me factor that 2 out. And I end up with 4x plus 3 all over 2x squared plus 3x dx. Now, for those of you that think that you can take an x and factor it out front, you're vastly mistaken. No variables are permitted to pass through that integral. All variables that match the variable of integration must stay inside of the integral. Remember, ultimately these are sums. Ultimately we can break this down into an xi. You can't pull those xi's out in front of the sums, out in front of the limits. You can't do that. So variables, as long as it's the same variable that is being dealt with in this portion, and the differential portion, it must stay inside. So that x cannot come out. Anyways, now I'm in a perfect situation because my u is exactly the denominator and my du is exactly the numerator with that piece of this can be put in the numerator. I can if I want to. extend my numerator like so, and put my dx there. So, and then I have 2 integral, have my u, there's du, and we know now that that's the natural log of the absolute value of u plus c. That equals 2 ln absolute value of 2x squared plus 3x plus c. So you see, just in one lesson, there's just a huge variety of integrals that you're able to deal with. Please forgive me, but I almost forgot to do the example that I started the whole lesson on. So let me do that now before I move on to definite integrals. So suppose you were given this integral, negative x sine of the square root of x squared plus 1. That whole quantity was divided by the square root of x squared plus 1 dx. Now, here is an interesting thing. We're playing the game of what could I let be equal to u, and hopefully I'll have a du that is compatible with the u that I've chosen. To me, but I've been doing this a long time, the square root of x squared plus 1, at the very least, x squared plus 1 as a u looks like a good choice, because I would have a u in 2 different spots. So I would have, I would have this x squared, I'd have all the x squareds taken out. But then if I thought about it some more, let's just see here. If I did u was equal to x squared plus 1, let's try that as an initial gambit and see what happens. So I'm going to let u equals x squared plus 1. So then du equals 2x dx. Now that's nice. It's nice to have an x hanging around and a dx, because I can rearrange this numerator to where that will be useful for me. I don't need a 2x, so I'm going to divide by 2 and have du over 2 equals x dx. After all, I need an x dx. The negative I would pull out front. So let's see where I'm at so far. I will have a negative in the front. I'm going to rewrite the integral before I make the substitutions. So I'm going to write sine of the square root of x squared plus 1 divided by the square root of x squared plus 1, and then times x dx. The reason I'm doing that is so that you can easily see where I'm making my substitutions. So this ends up being negative integral sine of u, sine of the square root of u, all over the square root of u times du over 2. So I've made my substitutions. Now I'm all in u land. What I can do now is I would take the 2 out front, and I would have this equals negative 1/2 the integral of sine radical u divided by radical u du. Now it's probably here a very tough spot that you're in, especially if you're not willing to do a multi substitution, which I could do right now. I could do this by introducing a new variable, say call it w, and I would let w equals the square root of u. So that's doable, but it's not something that I suspect is going to be very reasonable for this particular class, since you're brand new to this stuff. So while this can work, I'm going to leave it to you. For those who have the heart to go another step, I'm going to leave it to you to see what you would do to do that one. However, I will do it the way that I know gives me an answer, and I'll try to explain what I'm up to. Integral, I'll start over again, negative x sine of the square root of x squared plus 1 all over the square root of x squared plus 1 dx. I have a general philosophy on these u substitutions, and the general philosophy is to try to pick as big a possible a u as you can. Because this is some trial and error, expect to probably fail most of the time initially, and as you do more and more of these, you'll become more successful with your initial guesses. And they won't be so much guesses. You'll see enough examples that where you'll start to see patterns emerge and you'll become better. So what I said, maybe u be x squared plus 1, but I actually kind of wanted u to be the square root of x squared plus 1. Let me explain why. Because if u equals the square root of x squared plus 1, check what happens next. When I take the derivative, when I do du, the first thing you do with a square root is do 1 over 2 times the square root. This now gives me a replaceable square root in the denominator with du. Now I know I'm not quite finished with this because I have to take the derivative of what's inside of the square root. But when I get to this point, I'll tell you what, I'd be jumping for joy. Put my dx at the end of all that. Because for one thing, these pass out. But then look at my integral. There's an x dx in this du. I have an x and a dx. I have a 1 over the square root of x squared plus 1. A huge swath of the problem is absorbed by that simple du. So, let me do this. I'm going to pull out the negative like I did, and I'll rewrite it like I do the rest of them so that you can see the vast expanse of the du. So I have sine of the square root of x squared plus 1, and then I have times, I'm going to push to the back, what do I want to put? X over the square root of x squared plus 1 dx. Look at this. Now, I don't want to go up too farther. Let me go ahead and make my replacements now that I hope it's simple. I'm going to have sine of just u, which is always a desirable thing. And look at this thing right here. This whole piece after sine of u is just du. There's rarely any simpler of an integral that you can have, because we now know that the integral of sine is negative cosine, and there's even a negative out front of it. So we have this will equal cosine of u plus c. And then what was our u? Square root of x squared plus 1. This was cosine of the square root of x squared plus 1 plus c. And if I'm not mistaken, that was the original thing we differentiated to begin this whole lesson with.